Okay, so actually one of these formulas on this page, it may not look familiar, but you'll see in a moment it is. Throughout this week, we'll eventually describe where all the formulas came from. They didn't come out of thin air, but today I'm not going to be too concerned about that. Through the week, we'll figure out the origin of the brand new one. But we call these the kinematic equations. And what we use them for is situations with uniform acceleration, as it says right here. Now, as we did some graphing stuff recently, I described to you guys how in this course, an algebra-based course, we only deal with uniform acceleration. The graphical thing with that was that VT graphs, if you remember, I said in this course aren't going to have what kind of shape on them? Yeah. Curves. All right, that would be a curve on a VT graph would represent non-uniform acceleration, since we learned recently that the slope of VT graphs give us acceleration, right? So any time there's acceleration in this course, these are like kind of go-to equations for that, right? That will always be uniform. In the future, when you are in like a calc, when some of you might be in a calc-based one, or some of you that might take AP next year if you're still here, you got to be really careful when they are allowed to be used, because if acceleration is varying, then they're kind of no good. All right, so anyways, the first equation on this list is actually one you are familiar with, even though in this form it might look different. Way back when we only had that one little quiz so far. But when we did have that, on that quiz and leading up to it, some study guides, we learned a formula for acceleration. Who remembers it? Solve for A. It was A equaled what? You got to use it on that quiz. Yeah. No, that was velocity. Velocity was d over t. What was A? What's that? Nope. Velocity was v equals d over t. There was another formula we got to use for acceleration. And we actually will now call this formula the definition of acceleration, because we did write a word definition that the formula just fit perfectly with the word definition. Does anybody remember it? It was acceleration A equaled Vf minus Vi over t. How many remember that now? All right? That doesn't quite look like that, but think about this algebraically real quick. If I would subtract this Vi, because in algebra, you gotta be good with your basic algebra in here, especially from this point on. I can move this Vi to this side by subtracting, because it's added to this term, right? We should all remember basic rules of algebra. We can do anything to any side of the equation we want, as long as we do it to the other side as well, right? As long as we do it to both sides. That's like the fundamental rule of algebra. You could do something random that wouldn't even help you, but it's legal, like to add a billion to each side. You're allowed to. Wouldn't change the meaning of the equation, right? You got to do it to both sides is the main thing. So I could subtract Vi over to this side, and I would have Vf minus Vi. Then the t is multiplied by the a. I could move it by division, right? And wouldn't this equation be a equals Vf minus Vi over t? So that is one you're all familiar with. For whatever reason, probably no good one, when we list these four core kinematic equations, they're usually in these forms. All right, this one's solved for Vf, this one's for d, Vf squared, and this one for d. All right, and from there we usually, we run into nice situations where sometimes we can just plug right in, but we usually have to algebraically manipulate the formulas to solve for something that's not already solved for. That's what we're going to practice today, mostly, and into a little bit of tomorrow. There's no these don't have to be in this order. All right, necessarily, okay? However, for consistency reasons, every time I present them and list them, I will put them in this order just so we can refer to them easily. I'll call this equation 1, 2, 3, and 4. That way when we're doing problems and I'm like, all right, what equation do we do in this, solve this problem? You could just say 1, 2, or 3, or 4 instead of reading me out the whole equation every time, okay? Just makes it quicker. So there's no need they have to be in this order, although they usually are when they're presented in a textbook, but whatever. We're just numbering them to refer to them easily. And we've already run into all these variables in the past, right? We're just putting them into more equations, and we'll give you reasons for these equations as we go. But even though we have already identified them, I did throw in down here, just so we don't forget, what each one individually means. V subscript F, final velocity. V subscript I, initial velocity. V is obviously time, A acceleration, and D is displacement. Just a little note, stuff we learned in the past. We got to remember pretty much everything we learned up to this point at times when we use these equations. Remember that although D does represent displacement, if the thing never turns around that we're doing a problem on, distance and displacement are the, what did we learn? If an object never, and you just confirmed this again for the millionth time in your lab you just did, yes. Yep, they're the same magnitude, exactly. We just had some questions on your lab packet. You did two trials. One of them you didn't turn around, right? You just went straight out in front of the sensor and stopped, right? In that particular scenario, your distance and displacement should have been the same number because you never turned around, right? But then the other one, you did turn around, right? So the distance and displacement will be two different numbers. The displacement does differ there. The good news is 99.9% of the time moving forward, we're going to be dealing with problems or segments of problems that only go in one direction. So if that's the case, really, whether it's distance or displacement, it really doesn't matter all that much because it would have the same magnitude. So little details that always matter. Once we get tomorrow and throughout the week with dealing with acceleration and it as a given, we will have to go back and remember a lot of the stuff about direction of acceleration, and it doesn't mean speeding up or slowing down because sometimes we're going to have to slap a negative on it if appropriate. So, but starting right now, what matters the most is identifying the variable and knowing the equations are our tools to solving problems, basically. All right? Does everybody have that all written down? All right. So, whatever time we have left after I complete going over these, you can get started on homework. But the number one thing we're going to do is make sure we're good with our algebra rearranging this. So I want you to write down these scenarios, and this is what your homework is. All right? I just have it titled Algebraic Manipulation of the Kinematic Equation. I want you to take these four scenarios I present, and each scenario for each equation has three different things you got to solve for. Do this on a separate page. You do not need to upload this to Classroom for anything. If I give any points, I'll do a spot check, okay? Just in class. And I might do that, so make sure you have these done. So, like, scenario number one, solve equation number one for VI, A, and T. So there's three separate things there, right? Each one of these equations you're going to solve for several different variables. But pay close attention to number two, guys. In number two, look at it with me right up here. When I asked you to solve equation 2 for T right here, I have beside it what? When VI equals 0. And let me state something here. I'll come back to this. You could pause writing for a second because this is really important to pay attention to. All right? When we use equations and have to rearrange them, you're doing yourself a big disservice learning-wise by plugging in numbers first and rearranging. And there will be people that fight with me about this. And you'll say, well, it's easier. Why don't I do that? I'll tell you why. Most of you are probably in here more than likely because you're going to have to at least take one college physics, if not more. And in college physics, calc-based at that level, many of your problems then, past an intro class like this, require you to rearrange algebraically, and they won't even give you numbers. Many of the right answers will be expressions. If you don't get used to this right now, then you will struggle with that when it becomes much, much harder later. Okay? I give one exception to that. When any of your givens are 0, plug them in right away, because zeros wipe out a lot of stuff, right? And can make the rearrangement easier, and that's okay to make it easier if something's 0 and going to go away anyway. All right, but you're really just cheating yourself if you go through this course, do your work that I don't see, and just plug in numbers and rearrange with numbers. Because that's one of the most fundamental things that come out of this course, being able to rearrange all kind of crazy algebra stuff. Without that skill, you're going to be in trouble in college physics. All right? All right, so anyways, with that being said, going back to the scenarios, in equation 2, When you solve for t, plug in 0 for vi first, see what it wipes out and cuts it down to. It makes it easier. Actually, it makes, we'll point out exactly why when we go over these tomorrow. I'm going to go over every one of these one by one tomorrow, right when we get in here. We're going to go quick, but I'm going to go over every one of them. Not that long ago, I used to jump in assuming every student was really great at algebra. Well, many of you probably are. When I didn't go over the rearrangements to begin with, then the majority of the questions we had on like the first assignment actually using these was always algebra questions. So I always take day one of this to go through that right now to take care of the algebra. So that hopefully isn't an issue moving forward. So once you get these written down, I want you to start completing them. Don't skip steps. I know some of us are really good at basic algebra, as you probably should be at this point in your lives. But even when you're really good at something, when the equations get bigger and you start moving a bunch of things at once, that's when dumb mistakes start happening. Just go through this exercise and move one thing at a time, and hopefully you get the right answers. Right? This isn't check for correctness, but if I do some of these rearrangements tomorrow and you're not even close, you better ask questions of like, you know how I got something if you don't understand. Yeah. That's just an and. Right? Solve this one for VI, A, and T. Solve this one for VI, A, and T when VI equals 0. This one's VI, A, and B, and this one's VI, and T. Okay? As far as looking forward when we have our next quiz, which will probably be sometime next week. Remember, I don't make you memorize formulas in here. So, I'll flip back there in a second again. When we have any tests that involve the kinematic equations, these are what you get. You don't get any other rearranged forms of them. That has to be your skill that you are able to accomplish. You don't have to memorize these; they'll be given, but you do have to know how to rearrange them, and that's why this is important right now. So once you're done writing these, take the last 10 minutes to begin, finish for homework. After we go over them tomorrow, we'll jump in some problem scenarios with them. Bring your books, don't forget them. Those of you that need to finish the lab, you could hold off on this completely for homework and try to finish the lab in the last 10 minutes if you can.